Okay, we start our conference today with the talk by Sergey Gorchinskiy from the Stiklov Institute of Mathematics. He will speak about power structures on the Grothendieck ring of varieties.
Thank you. Maybe you could put the presentation on screen. Okay. So first of all, I would like to thank the organizers for the invitation to this next conference. It's really a great honor for me to speak here, and I apologize that I skipped all the other talks. Because there was a parallel conference in Stiklov Institute where I was an organizer. And then I would like to express my admiration and respect to Sabir M. I think I first met him at Penn University, and at that time I had some course on differential geometry in Moscow State University where I understood nothing because there were too much formulas with gamma I, G, K that algebraics cannot understand. And you gave some short introductory course to differential geometry taught in different manner in independent university, more geometrically, more invariantly, and more algebraically, and I hope I could understand something. So thank you for that. And actually the topic of my talk is very much related with power structures introduced by three people. Two of them are present here, Ignacio Luengo and Sabir M. And the story that I came to this was like that. So there was some conjecture made by Galkin and Schinder, maybe more than 10 years ago. Then together with Valery Lunz and some other co-authors, we tried to do this conjecture, and we proved it several years later. And so there was some strange formula. And then I came to papers by Sabir M. and co-authors with the notion of power structure, because unfortunately I didn't know this notion before. And then I understood that actually this is the reason why the formula holds, why the conjecture holds at all. And then there was an idea that maybe what could rephrase the conjecture in terms of power structure. Well, to rephrase was simple, but much harder was to prove it in terms of power structures, like our proof with Lunz. And this required some hard combinatorial work, and I stopped for a while. And then I was happy to meet a very brilliant young student from Fistech, Danila Demin, who was a gold medal at IMO, yeah, and so for him combinatorics was just a piece of cake, and together with him we could manage this approach, and so I will try to explain all this. Okay, so but since of course I would not like to explain to Sabir M. what is a lambda structure, or to you what is a power structure, but since there are other people, so maybe I will start with introductory material. So throughout the talk, R will be a commutative ring with unit. Let's consider the ring of formal power series, as usual. And so in this ring, we can consider these subset of rings starting by 1. Of course, this is a multiplicative group. We can divide by powers like that. And there is an evident surjective homomorphism from this group. Sometimes this group is denoted by W because this is an additive group of the ring of bit vectors. So we can project. Well, the free term is always 1, but we can consider the coefficient by t, in a sense the derivative, and this is evidently a group homomorphism, yes. So a lambda structure, for short I will say lambda structure, usually it is called a pre-lambda structure, because for lambda structure one requires something more. So a pre-lambda structure, or just a lambda structure on a ring, is the following. It's a section of the homomorphism pi. So it's a homomorphism lambda, such that pi lambda is identity. What does it mean explicitly? Give a section like that means giving a map from R to the set of power series. So for each element from R, we should specify coefficients of the corresponding power series. Let's denote the coefficient by t to I by lambda I. So we have lambda of A, where A is from R, is some series with coefficients depending on A, lambda I on A. But of course, lambda I are not homomorphisms themselves, but altogether they must give a homomorphism to the group 1 plus t R of t. So if you open bracket, it gives... А здесь можно нажимать, да? Тут указка есть, нет? Ну хорошо. Курсорчик это как? А куда нажать? В смысле, сам себе. Okay. So here you see there is this explicit formula. Sometimes one call this a lambda structure. This is very explicit. So examples there is a trivial example. Once your ring contains the field of rational numbers, well, there are many more lambda structures, but there is always one trivial lambda structure when you just exponentiate, right? If you take exponent of AT, of course, it will be a group homomorphism, but you require denominators here. Now, let's consider the simplest example of a ring that is not Q, that is Z. Then in this case, there are not so many homomorphisms from Z to any other group, so it's clear that all of them have the same, the following form, G to A, where A is some integer and G is some fixed power series which must start by 1 plus T, because you remember it should be a section of pi. So there cannot be other coefficient by T here, just one. Now, an essential example is given by, this may be one of the roots of K groups. For simplicity, consider a finite group and consider its finite dimensional, the simplest possible case. Finite dimensional complex representations. Each finite dimensional complex representation, of course, decomposes into a sum of reducible components. Let's consider a free group generated by isomorphism classes of irreducible representations, and so each representation gets a class in this K0 group, and of course this group is a ring with multiplication given by tensor product of representations. Tensor product of reducible ones does not need to be reducible, but we can decompose. And so this is a ring, and it's typical that on rings of that sort we get some nice lambda structures, because here the lambda there are several lambda structures. One of them is given just by taking symmetric powers of representations. Why is it a lambda structure? Because there is a Kunin formula. If you take, this is the equation for the lambda structure. If you take symmetric power of direct sum, which corresponds to the summation in this ring, direct sum of two representations, then it decomposes like that. By the way, if you were taking a tensor structure, of course there will be no decomposition like that. So it's important that we can transpose elements in tensor products. For example, for an alternative power, they will be the same analogous formula, and it will also give a different but also lambda structure. Okay, well, probably the roots of lambda structures are from topology, because one can repeat absolutely the same for vector bundles on manifolds or on algebraic varieties. And maybe this was the first, I don't know, example of lambda structure by Grothendieck or someone else. Okay, so now given a lambda structure, very simple lemma. We obtain an isomorphism, kind of exponential, between series that start by T with addition group law and the group that we already considered, 1 plus T multiplicative group, 1 plus T R of T. How is it done? Let's call it exponent with index lambda. So a series like that is sent to the following. So if the series were just linear, B1 T, then we should apply lambda of B1. If no, if you have B times some T to I, then let's make this the corresponding change of variables T to I after we apply lambda. So it's altogether it gives us like that. So the sum of Bi Ti goes to product of lambda of Bi. Each lambda of Bi is a series in T, and we should plug in this change of variable. And then we multiply all together. It's very easy to see that the product converges in algebraic sense, that if you want to calculate the coefficient by T to 100, then you have only finitely many terms to add. And also it's very easy to see that it's an isomorphism, because how do you do the inverse? You consider a series like that. It starts by A times T. Okay, then let's divide by exponent by lambda of AT. Then it starts. It gets a shape 1 plus some A2, new A2 times T square. Okay, let's divide by lambda of A of T square, and like that we obtain inductively coefficients Bi. The main point of the whole talk is that it is very explicit to do it from left to right, and it is very to prove that it is an isomorphism, but it is very hard to give an explicit formula from right to left because of this induction process, which gets very complicated after several steps, right? Because we always additive group, of course. Additive. You see, here we add, then goes to multiplication of the right by this form. Let's denote this mysterious inverse by logarithm lambda. so for example, if for the silly lambda structure, for exponential one, this will be really, exponent will be really just taking exponent of a series. So that's why it makes sense to call it exponent. Now, for example, so what does it mean? How does it work explicitly? From left to right, we can give a closed formula for coefficients. It's very easy. You just open brackets and you calculate the coefficient by t to n. You see that to get the coefficient by t to n, you need to understand what comes from first term in this product, what comes from second term in this product, and so on. And since the products are, the arguments in the product, the parameters are twisted, the t is changed by t to I, there comes not just decomposition of a number into the sum of numbers, but here comes partitions. So we should decompose n as a sum of not just i's, but some sigma I times I, right? Where this I correspond to this change of variable t to I. And then after you open bracket, you get this very simple and nice formula for the coefficients. And so, for example, A1 is B1, A2 is B2 plus lambda 2 B1, A3 is B3 plus B1 B2 lambda 3 of B1, and so on. Each time you can easily see AN starts by Bn plus some lower terms. By the way, it also shows that it's an isomorphism. You express AN by Bn inductively. Yeah? Okay, so now I would like to, it's a shame a bit to speak about this by the creators, but for all the others, I would like to explain what is a power structure. I'm an algebraist, so I will speak a bit in an algebraic way, but absolutely the same that was done in the papers by Sabir M, Ignacio, and Melle-Hernandez. One can say like that. So we have this isomorphism. Note that it has three simple basic properties. First, it commutes with pi, with projection to the first coordinates, just because, as I said, A1 equals B1. So the coefficient by t doesn't change. Secondly, it commutes with the change of parameters. T goes to t to n. This by design, because here we make this simultaneously these changes. So if I replace here by t to the n, then everything here will be replaced again by t to the n. And next, it is t-edically continuous. It's clear, because if this series starts by t to 100, then this will also start by 1 plus t plus 100, but so on. So these three properties. Now, on the left-hand side, which is not just group with addition, it has trivially another structure, multiplication by R. As an R module, it's a very simple module. It's just a countable product of copies of R. So, of course, like that, yes, A times some AI BI, some BI TI is like that, just term-wise product. So, as a module, it's very easy. But then, yeah, also this structure definitely commutes with these three things, with pi, with change of variables, and this theoretically continuous. Then, just trivially, this structure on the left can be transposed to the right. From the point of commutative algebra, nothing happens. We have the same module. As a module, it is isomorphic. But it's interesting from the point of view of explicit formulas, how does it act? So, X lambda defines an R module structure on this group, multiplicative group. So again, given lambda, we get some way to operate on this group by elements from R, which have the same three properties, because everything here was having it. So explicitly it's like that. Yeah, denote it like that. Well, for me, I cannot think that you should exponentiate an element from a module to an element from a ring. So I will just usually not denote it usually as multiplication from an element from a ring by an element from a module. So let's write it like that: A times F, and this times depends on lambda. So lambda is in the index. So we first send F from right to left, multiply just term-wise by A, and then send it back. It's easy, like that. This is almost the notion of the power structure. I will give a formal definition on the next slide. So, for example, if R is Z and our lambda structure was given like that, then you remember there was this example. Then A times F, A is an integer, is just F to the A. And we see here, so first of all, we see that it's really a power of a series. And secondly, we see an effect that various G define the same Z module structure. And actually, there is only one possible Z module structure on anything, on any abelian group. Huh? Well, each time is just any element from the ring, from Z here. They run through all. for any A, it holds. A times F is F to A. Both times you have counter for all. Спасибо. This holds for any A. This is the definition of lambda structure. Here there is some power structure where you should multiply by an arbitrary element A. And this formula holds. Both are for any A. Okay, so now the definition. Star lambda, right. It's star, sorry, I should have put star lambda, yes, you're right. Star lambda. Okay, now, so what is the power structure? I will consider only so-called finitely determined, so I will omit this. The authors, they defined first the notion of a power structure and then an additional property of being finitely determined. I will collect it all together. I will not consider other power structures. So a finitely determined power structure on a ring is what we just got, is the structure of an R module on this abelian group with these properties. By design, they all come from this construction. But this is a way to pronounce things without involving any lambda structure. So this is really a great notion. And Sabir M, Ignacio, and Melle-Hernandez, they applied it to many questions in keynote of variables. Well, as far as I understand, one line of applications is as follows. So sometimes there are homomorphisms from ring K0 of varieties. K0 of varieties I will speak later about what it is. To some other rings, for example, to Z, just Euler characteristic with compact support, or probably to series in two variables given by Hoche theory, or someone else. Already know that it commutes with power structure. Then if you have any formula in K0 of R in terms of power structure, it automatically gives you the corresponding formulas already with values in the ring where your motivic measure is sent to. And so people were, some previous authors were proving some formulas of that sort after application of the homomorphism from K0 of varieties to somewhere else, and they did it on the geometric level, on the level of K0 of varieties, right? Am I correct? Maybe at least partially. Okay, so it got really a lot of applications through years. It appeared in 2004, I guess, or maybe earlier. Actually, what I will do will be absolutely the same way. There were some formula with values in some awkward ring K0 of DG categories, and then I realized that one can lift to some power structure expression just geometrically for K0 of varieties. Окей. Так. А тут немножко. Ага. Можешь пошевелить? Ага, отлично. Okay. So, as I said, there is bijection, any power structure, что-то опять, is obtained like that from a lambda structure, but different lambda structures we saw can lead to the same power structure. So, more precise, there is bijection of sets. The set of lambda structures is a product of the set of power structures and the set of series starting by 1 plus t. Starting by 1 plus t, the bijection is as follows. So we send lambda structure to the corresponding power structure and the value at 1. As we defined lambda structure, it is not necessarily a ring homomorphism in any sense, so it can send 1 to an arbitrary series starting by 1 plus t, so G. And vice versa, given a power structure and G, you obtain lambda structure very easy. You just should multiply your G by A. Clearly it's bijection. Well, it's all very beautiful and simple. Clearly two different lambda structures define the same power structure if non leave this holds. Well, now the problem is twofold. So given a lambda structure, find an explicit formula for logarithm lambda from right to left. And it's clear that it's a related question because formula for power structure relies on lambda, on log lambda. So also to find explicit formula for star lambda on arbitrary ring. Okay, so I will address this problem. So in which sense find a formula? What does it mean formula? It's clear once you think that you should think about free or universal lambda rings because formula should be something universal. Let's spell it out. What is a free lambda ring? It's clear that, so first let's define lambda monomial. Lambda monomials, so we consider free lambda ring generated by some set U capital. So free lambda monomials, they should just contain these letters, U. Also, they should be closed under taking products. and also they should be closed under applying operations lambda I. So for example, uv or lambda 5 of lambda 3 of u times v or so on. Yeah, these are monomials, and so a free lambda ring z of variables u from u capital with subindex lambda, of course. It's a free lambda ring. It consists of all possible linear combinations of these monomials. It's a free object in the category of lambda rings generated by the set u. So what we want in these terms? We want, so let's consider a universal. We want to find a logarithm. Logarithm of what? For any ring. It means that we should consider a free lambda ring generated by formal variables that are coefficients of an arbitrary ring like that, or an arbitrary series like that. So we consider free lambda ring generated by AI, and then we take logarithm. It becomes an element from this ring, and we want to find its coefficient. Its coefficients by t to n, by each lambda monomial of A. And similarly, as for power structure, we should also add one more element m and consider free lambda ring generated additionally by m, and then we're interested in z coefficients by all lambda monomials in this series. Okay, so now if you try to think how to express combinatorially these things, you come to trees, because, well, you can express by think like that, lambda, say, 3 or lambda 2 operation, and then make a tree. But tree should be marked, so you come to some combinatorial objects, and you can try to work with them. They are natural, but they are not so useful. And so the insight of this Danila Demin, this guy, was to consider a bit different combinatorial structure. In a sense, it's some kind of like a resolution of singularities of the structure of the evident one given by trees with marks. So let's consider the following combinatorial structure. Now a bit of combinatorics. So let's consider forests, namely the joint union of trees, such that all trees are rooted. For each ti, I fix n vertex, vi, root. And on the set of leaves, I want to fix a function with non-negative natural numbers, such that certain conditions are satisfied. What is this condition? Condition says the following, that first of all leaves should have the same height. All leaves should have the same height, the distance to the root. Next, and the second condition is that there should be no ineffective generation. So for each generation, at each generation, there should be at least one member which have at least two descendants. Let me draw. Yeah, it's very easy, but let me draw. So for example, this is from F, and this is not from F, whatever I put here. Yes, and for example, note that this is from F, because at each generation, sorry, like that. Yeah, this is from F. Okay. Now given a forest like that, let's define its weight as the sum of weights over all leaves in over all trees. And for each n, let's consider just three. For each n, let's consider forests of weight n, fn, and inside it, let's consider trees. So trees that satisfy this star condition. Now, a very simple observation is that for each n, the set of forests of weight n is finite. Why? Because of this generation condition, at each new generation, we get at least one new descendant. Each descendant, in a sense, it increases the total weight by one, at least one. So if you have weight n, it cannot have more than n generations. And after you have bounded the number of generations, of course, number of vertices in the generation is also bounded by n, then you have only finally many possible trees, forests. Yes. And also an important thing, the main non-trivial thing here, is that even if a forest belongs to F, it is not necessary that its component also belong to F, because they might be just like that. This is from F. This is not from F. But here I have this. So this is from F, right? Because there are no non-effective generations. But all non-effectiveness is in this component. So this component itself does not satisfy this condition. But to get a right answer, we should really consider forests that satisfies this condition altogether, collectively, overall forest, not each tree individually. Otherwise, the answer will not be correct. Yeah, what I spelled is some explicit bound, but that's absolutely non-effective. Of course, it can be much stronger, but we are not interested in explicit bound. Yeah, okay. Now, the trick is to consider free lambda ring generated by all trees, not forests, satisfying this star condition. And then I would like to define, so for each tree, there is a formula, an element in this ring, P, T. Now for each forest, I also would like to define an element. I might consider just free lambda ring generated by forests, but then I will not get the formula that I will speak later will not be correct. So I want to consider ring freely generated by trees, and then for each forest, I define its lambda polynomial of trees as follows. So I decompose it in two components, and components may be isomorphic or maybe not. Isomorphic counting the weights as well. So just the same components counting the weights. And if you have several components repeated, so each component, for example, Ti is repeated ni times, then I consider P applied to Ti almost, and I apply lambda ni. But the only point here is that, as I said, Ti itself may not satisfy the star condition. But clearly, if any tree does not satisfy the star condition, it means that there are non-effective generations. So generations, you had some tree, and then there are some generations where each member have precisely one descendant. You can just contract it. Contract in a unique way all these non-effective generations. And after you contract all of them, it's a unique operation. You get some tree of smaller height of the same weight, satisfying star condition. So let me give some examples. So for example, well, if we have some two different trees, say, then in this case we have two different components. So we should just multiply lambda applied to components separately. This component also already satisfies star condition times, and this component does not. But after I contract it, I get just 0.2. Point with mark 2. Okay, and for example, I can also get square of the same lambda monomial if I have two different components which are non-isomorphic. They are non-isomorphic. You see, they are non-isomorphic. So I should multiply separately lambda monomial associated to this and lambda monomial associated to this. But after I contract them, they become the same. So I will, after all, I will get P with index like that, 1, 2, square. No, very top edge is allowed to have one. Sorry, I should have said very top edge is allowed to have one descendant. No, I should. Yeah. You're right. Oh, sorry. You're right. Wait, you're right. And but sometimes if I have the same components, you're right. The same components, then I will get lambda 2 because they are repeated twice. P. What? No, why lambda? Lambda appears when you have several components repeated. I was denoting by P, right? It's PF. In this first line. Sorry. This was a mistake. Yeah. This. Thank you. Yeah. Yes, thank you. I'm sorry. It was denoted by P. Sorry. This, of course. You're right. So now the key statement. Key combinatorial statement is as follows. So with various in this ring, which is a lambda ring, it's a free lambda ring, there is the following identity between only one particular element and another particular element. So if we take this suitable element, so let's consider the series. It's an additive series, so starting by t, and the coefficient by t to n is what? It's an alternate sum over all trees, not forest, of weight n, admissible with star condition, admissible trees of weight n, alternative sum of with respect to their height. And if we take exponential lambda here, there is a canonical lambda operation. If you take exponent lambda inside this ring, we get the alternative sum over all forests. In general, it's very natural that if you exponentiate something over all trees, you get something over forests. But unfortunately, it's not that easy because of this technicality, that it's not true that if you take any forest like that and you decompose it into pieces, then there are trees like that, as I showed. You should contract. And these combinatorics with different contractions lead to some additional combinatoric technicality. Yes, but as I said, if you require at the beginning that all components are like that, then the formula will not be true just. Okay. Yes. Some questions so far? So how does it apply to the question above? So somehow the main results are as follows. So let's project from this ring, abstract ring generated by trees, to the ring generated by coefficients ai, where coefficients ai are coefficients of the series that we would like to take logarithm of. And here the trick is to consider the following homomorphism. Let's define it's easy to define a homomorphism between three lambda rings, right? Because you need just to specify where do generators go. They can go arbitrarily, and then everything is uniquely determined to be a homomorphism of lambda. Спасибо, super. To be a homomorphism of lambda structures. So let's specify where do things go. So it's uniquely determined by the following two conditions, that lambda of a point with mark I should go to ai. And the second condition is if I take some tree, then I should take an x and cut its root. It becomes being decomposed into, it becomes a forest. This forest must be admissible, satisfy the condition star. Then this forest gets a polynomial in the string I already defined, pf. It is of last height, and by induction I presume that I already defined what is where pf should go. So I define this homomorphism on p t by induction on the height of t. For example, let's consider, so weight 1. In weight 1 we have only this possible thing, and it goes to a1. Weight 2. In weight 2 we have also this thing, of course, but we also have this admissible tree of weight 1, of weight 2. And it goes to where? Where does it go? So I cut the root. I get two copies of the same tree marked by 1. So I must apply lambda 2 operation of something where star 1 goes, so of a1. Now n equals 3. N equals 3. Of course this. What else do I have? Of course I have analogously just like that, and similarly it goes to lambda 3 of a1. Which other trees? I said the set of trees, forests even, but of trees of course is finite. So of course I have a tree like that. Where does it go? After I cut my root, I get two different trees, and so it goes to lambda a1 times a2. There is one more tree, namely like that. you can easily check that there are no other ways to get weight 3 satisfying this degeneration condition. Where does it go? I cut my edge, then I get two different trees. Okay, I should multiply them. This, then I should contract, so it goes A1 times, after I contract this, I get lambda 2 of A1. Okay. Now, why is it funny, this homomorphism? It is funny for the following reason. The left-hand side, well, it was alternative sum by trees, so it goes to alternative sum now of polynomials lambda within this tree. But the point is that the right-hand side goes very neatly to this series. Why is it the reason? The reason is very explicit and combinatorial, I would like to explain. So the reason is the following, because on the right, as you remember, there was an alternative sum over all forests, or the alternation was over height of the forest for each given weight. And now the trick is that if you consider all forests of 8n, each forest is very simple, is either a tree, either it is not a tree. So it is, the set is decomposed into disjoint union of this and the complement. But if you take a complement, so it's some forest, you can always do the simple thing. You can always join all of them together. And after that you get what? You get a tree of height plus 1, the same roots and the same weight. So you see that there is bijection with what? There is bijection with T n, but the point is that you are not getting only one tree, namely one vertex, because one vertex is the application to empty set. So without point with mark n. But this changes height by 1. And so after we take alternative sum over all forests according to the height, we see that this this cancels with this Tn without a point, and only one point remains. One point goes to An. So all forests, they cancel out. Okay? It's like that. Now for the explicit formula for power structure, we should also add this M, and so I will not maybe spell out it too much, but it's already an easy calculation from this formula and the previous one, that if you define a bit different homomorphism mu t, where mu t is old lambda t times m, then the formula is like that. Okay. So now I have 10 minutes, right? Very good. Now back to Grothendieck rings of varieties. So very quickly I will, I think most people here know what is it. So we consider some geometrical application of this. So consider Grothendieck ring of varieties over a field which is defined as the following quotient, very well known. So free abelian group generated by isomorphism classes of varieties subject to the scissors relation. It's a ring with multiplication given by product of varieties. And well, for example, you have some funny relations. Hyperbola, for example, can be realized both as a hyperbola on the plane or a complement to a point on a line. So you get relations like that, for example, and so on. So very, very, very interesting ring studied by many authors. And so it's interesting to study the ring by specifying homomorphisms to other rings. And the homomorphism to same other ring is sometimes called motivic measure. So it's a way to satisfy this condition, also the condition that on the product should be the product. Some basic example of a measure is given by Euler characteristic with support. And some other example, very well known, over finite field is given by the number of points. Of course, if you decompose a variety, the number of points adds. And so why symmetric powers are so interesting? Probably initially the motivation was from zeta function. There is a veil zeta function defined by veil for any variety of a finite field, defined like that. And you can easily see by definition that actually this is this motivic measure mu sharp applied to the sum of symmetric powers. And so the idea maybe by Kapranov was try to leave everything that was said about where it has a zeta function to the level of k0 of varieties. Of course, not everything can be lifted. For example, rationality fails, but still, it's interesting to consider series with coefficients given by symmetric powers of varieties. Symmetric power is the quotient of a symmetric group. And actually, it's also, so it came to the business, and immediately we see that these classes of SI define a lambda structure on k0 of varieties. This is the main point. Well, again, by Knut formula, and so Sabir M, Ignacio, and Melle-Hernandez. So this defines a power structure on the ring of varieties. And I don't know how one can come up, but there is a fantastic formula. It's a complicated formula, but very beautiful and efficient in applications. An explicit formula for the power structure on this ring. I must confess I cannot reproduce it by heart, but well, it's really impressive formula. And now there is what I would like to discuss at the rest of the time. There is an equivariant version of Grothendieck ring of varieties. You also considered it. I will consider a bit different version. So the definition goes to Daniel Berg, which was our co-author with Valery Lunz when we were studying this Galkin-Schindler conjecture. So he came up to the following explicit definition. It's by him. So the idea is the following. First of all, a naive thing is to consider K group not of varieties, but of varieties with action of a fixed group G, absolutely similarly. But then, of course, it is not a ring. And it's actually nice. It's actually natural to collect all groups together. So how to collect? We might take just the direct sum, and it will be a ring. But it's not so interesting. It has not a sticky sense. So one should collect altogether these groups, additive groups, k0 of varieties with action of G, and then take the formally it's a sum over isomorphous classes of finite groups, and then take the quotient over the following relation. Now, this is the this is invention by Berg. So the relation is as follows. Suppose the product of two groups acts on a variety, and suppose that one of the terms H, let's say, acts freely. Then I should have said the notation is like that. If G acts on X, we propose to define the class, denote the class like that, X in brackets with upper index G. There are various ways to define, to denote it. Well, I propose like that. So then the class of X with action of H times G should be the same as the class of X mod H with action of G. This is a very neat way to collect together several things. Yeah, multiplication is given now like that. Let's compare with the construction given in the papers by these people. So they considered, you considered a bit different quotient over a bit different relation, which is absolutely natural. Relation is as follows, that after we take induction, the equivariant class of variety does not change. So given an action of H on Y and embed H into a bigger group, take the induction of variety, then the action, this with action of G is the same as Y with action of H. It's not a hard exercise to show that the relation, apparently they do not look similar, but actually the relation I gave before implies this relation. And but it also adds one more relation. For example, if just one group acts freely on a variety, then the class of xg is the same as the class of the quotient. This apparently is not in the relation given by induction, but for the formula that will hold, we need it. And it is natural also to consider this for some more scientific reason, because actually, as was noticed by Berg, there is a natural homomorphism from K0 equivariant, or this ring, because this maps to prime ring maps to this ring. So from K0 varieties equivariant defined in any way, there is a homomorphism to K0 of Demin stacks, namely that sends the G equivariant class of X to the class of the quotient stack. And this explicit relation provides an isomorphism of the rings. So you can, on the right, you can, independently of any way, you can just define K0 of the Riemann stacks in the same scissors relations. And this will be an isomorphism. So this is a way to overcome all difficulties related to definitions of a stack or so on. You can do it explicitly just like that. Okay? So we will further we'll speak about this ring. Now on this ring there is a lambda structure. Of course, if you think about the Riemann stacks, then you just define lambda structure as a symmetric power of the Riemann stack. if you say in terms of varieties vector of G, it should be like that. You just say x to I, then on this group, on this variety x to I, x G to I, term by term, and also get x the permutation group. Altogether, it gives you the action of a semi direct product of sigma I by G to I. And so let's consider xi keeping this action of a group. We are not taking quotient, it's just variety with keeping track of an action. And so there is a Navier homomorphism from K0 of varieties to K0 of equivariant varieties. So just consider variety with a trivial action of a trivial group. Of course, everybody considers it. And it's clear that it does not commute with the lambda structure, just because symmetric power is absolutely not the same as taking the Cartesian power and keeping track of sigma I, because you have stabilizers. All combinatorics with this stratum comes in. And so it doesn't commute with lambda structure. Now the main and the initial motivation was for all of these formulas is the following theorem, that actually it commutes with power structures. Well, I didn't know how to prove it before these formulas appear. After one has these formulas, it's not hard to prove it. So application is, yes. So we can also reproduce the explicit formulas for lambda structures, for power structures, for power structures as we have put in here, on the Grothendieck rings of varieties or on equivariant varieties. So this formula can reproduce. Also, actually, this statement almost immediately implies Galkin-Schindler conjecture, and it lifts it from categorical level up to geometrical one. And just last remark, that the main reason why these formulas apply is the following, that so here we have no geometry, it's for any ring, but here we have combinatorics related to these forests. These forests, you can think about this forest as follows. So for example, only one way here, only weights one for simplicity. So we have some set of 3 elements here. Then we should say, how do we decompose it into subsets? Then we take one more decomposition of the subsets into subsets. And so after all, you see that each decomposition into subsets corresponds to a sigma invariant strata on the combinatorially corresponds to a sigma invariant strata on nth Cartesian power of a variety. And forests correspond to chains of embedded stratum. And you know, if after you sum something over chains of embedded stratum, things cancel out, and you get some geometrical interpretation of all these formulas. So after you plug in this alternative sum over forests and you apply it to this case, you come to strata on Cartesian powers, alternate sum of stratum, or chains of stratum, and it all gives you the formulas from my paper and mainly this application. Okay, so thank you very much, and I wish Sabir Zhitvich many happiness and many new successful results. Thank you.
Thank you very much. Are there any questions?
Schindler, Zhenya Schindler. The conjecture was the following. So one can consider K0 of varieties. Now we see that in the middle one can consider K0 of varieties equivariant, but at the moment it was not came in. Then one has one more homomorphism to so-called K0 of DG categories, which I will not like to define. It's related to derived categories of smooth projective varieties. So one has something called categorical measure. And they would like to compare zeta function of variety, which is given by, as you know, Si T to I, zeta function, Kapranov motivic zeta function of variety, or lambda structure just, and compare it with, here also for DG categories you can consider alternative powers defined by Kapranov, Getzler. So here one also has some power structures, and they are defined so that these homomorphisms evidently commutes with these lambda structures. So if you want, you can not think about DG categories, you can think just about lambda structure, symmetric lambda structure here, like you defined it. Because it's evidently is sent to this lambda structure categorical one. But at the moment, this was not in the game. So there was some categorical lambda structure. So here we have mu cut of x, and then we take this, I don't know, categorical symmetric powers. T to I, let's call it lambda I, categorical. They would like to compare it. After you make calculation for a point, you see that, so for a point it's related, for a point these things are related for a point. If you consider a point, then this is the class of the category of representation of, if I take lambda I, of ith symmetric group. The category of representation of ith symmetric group is semi-simple. It's like you should just take several copies of category of vector spaces. Yes, as many as partitions you have. Yes, as many have reducible representations of symmetric group. And so for a point, it gives immediately the following formula. So let's call this zeta categorical of variety. So this takes values in here. And then after you consider point, you may make the following conjecture. Conjecture that it's a product overall I greater or equal than n of the mu categorical, we should apply mu categorical, of the motivic of x t to y. And you see, it's really a formula very much related to the power structure, without knowing what it is. And well, now it is just, we just show that this commutes with power structure, then this just even with lambda structure, so the rest commutes with power structure, and then it's just easy to see that it holds. Well, with Luengo, we were proving it by considering symmetrical decompositions of varieties and so on.